All right, welcome back, everyone. So last time we left off on introducing the transistor. And we're going to continue with that today and cover kind of the terminals that a transistor has, some of the things that we need to be aware of when we're using it, and kind of how the operation works. And then we're going to break it down into a transistor's modes of operation, and we're going to see how we can analyze it. So the transistor we're going to be looking at first is known as a BJT, and this is kind of our very basic general purpose transistor. And this is usually where people start, is with these BJTs. That stands for a bipolar junction transistor, and this just refers to its construction. And like I said, this is kind of the beginning general purpose transistor. There are thousands of different types of transistors. Now, when we look at this bipolar junction transistor, or this BJT, I'm going to go ahead and actually draw up the junction diagram. And I'm going to use the junction diagram in a circuit to try and try to elaborate on a few of these pins. Now we're going to connect a resistor up to the top. And we're going to give ourselves a voltage source attached to that resistor. And we're going to do the same thing for the base. And down at the bottom, we'll connect this up here, and we'll refer to this as our ground, our 0 volt. Okay. Now, over here at the top, we have the collector. In the middle, we have our base. And down here, we have our emitter. Okay, so I'll go ahead and write those out. We have C for collector, B for base, and down here we have the E for emitter. And those are the 3 terminals that we get with almost every transistor that's out there. Okay. Yes?
This is a dumb question, but is the transistor in series or parallel with the first resistor?
With this guy?
Yeah.
Is it in series or parallel? So when you're talking about a transistor, it's a 3-terminal device. It's a little hard to say what's in series, what's in parallel. But what we can say is that there is a junction coming from this word bipolar junction transistor between the base and the emitter. So this resistor that I haven't labeled yet, which we're going to label as R sub B, is in series with the junction that's created between the base and the emitter. So if you look over here, this PN junction creates a diode, right? So this is kind of what I'm going to get to, which is RB is in series with the junction, this diode that's created between the P and the N-type material over here. Does that make sense?
Yeah.
Yeah. And the same thing over here, we have a junction between the collector and the emitter. This resistor up here is in series with those. Okay? So I'll get to those. So we're going to label this resistor, since it's connected to the base, as the base resistor. And this resistor that's up here is connected to the collector, hence we'll call it RC, the collector resistor. And this voltage source that's applied to this resistor that's connected to the base we'll refer to as VBB. And VBB because this is the base bias voltage source. And over here, we have VCC, which will be the collector bias. Okay. Okay, we have a circuit here to drive the base, and we have a circuit here that is applying a voltage to the collector. And as I said last class, please remember at the end of the day, what this transistor is doing is we are controlling this large main current over here flowing through the entire device with a very small base current. Okay, so this is controlling the amount of this, right? And so we'll label this as IB for the base current. And this main current that's going through here is going to be the collector current, or IC. Okay, so we have a collector current being controlled as far as the magnitude. The amount of IC that's flowing through this entire device is being dictated or controlled by the amount of the base current that's entering this device here from this side. Okay, now I drew it specifically this way as opposed to, and maybe not a bad idea to keep in mind what the original schematic symbol looks like. Where we have our base, our collector, and our emitter. And in fact, this will be the only time I ever draw it like this, is just for kind of explaining a few of the things with these terminals that's going on over here. And by terminals, I mean the base terminal, emitter, and the collector. Okay, now let's go ahead and also establish a couple of other voltages that we're going to be interested in. I'll shift this over. So we have a voltage between the collector and the base. Okay, so this is the collector to base voltage drop. So we're just going to be using our subscript to denote the voltage between the collector and the base in this case for VCB. We also have a VCE. This is the collector to emitter voltage drop. And we have another one, which is the voltage between the base to the emitter, so VBE. Okay, so now that we have all of these terms out of the way, we can start discussing what happens between these terminals. Now, the first thing that I want to draw your attention to, and This is the base to emitter junction. And as I've said, it's IB that controls or dictates the amount of IC. So let's go ahead, let's look at what's happening between the base and the emitter. Well, what do we have inside the device? We have a P to N junction. And just like when we covered the junction diagram for the diode, we have a diode that's been formed over here, right? We have a P and an N right next to each other. So over here, we get a depletion region. We have a barrier voltage we're going to have to exceed if we want IB to flow through it. So I'm going to go ahead and draw this. As such. Okay, we have a diode that's formed, and we get everything that happens when you create a diode between 2 points. Okay, so in order to get current to even flow through this, in order to get any IB, we're going to have to forward bias this PN junction. So we need to have a higher voltage here than over here if we want current to go through this. Now, this transistor is created in silicon. So just like our silicon rectifier diodes, we also have a forward voltage that we're going to have to exceed between the base to the emitter. And that's going to be taken to be a nominal 0.7 volts. So we're going to have to not only apply the polarity in the correct direction, but we're going to have to exceed that 0.7 volt forward voltage drop if we want IB to be greater than 0. So let's go ahead and let's say that. So now we're going to talk about the base emitter junction. And I'm just going to say it acts like a diode. And by that, I mean we have to forward bias it. As well as exceed 0.7 volts. Now, you could also construct a transistor out of germanium, and the first transistors were, because germanium seemed like an easier thing to work with. And in that case, you would have a smaller forward voltage drop because the nominal forward voltage for germanium constructed PN junctions would be more along the lines of 0.3 volts, 0.4 volts, around there. But all the transistors we're going to look at in this class, we're going to work with silicon-based diodes. Okay, so we're going to take that as having a forward voltage of 0.7 volts, and so we're going to need the voltage between B and E to be greater than 0.7 volts if we want IB to be greater than 0. Okay, now I'll also say, keeping in theme with this idea that a small base current controls a much larger collector current, we should limit the amount of base current entering this device to be in the microamp range. Okay, so microamps going here, milliamps going through this. Okay, so that takes care of the base to emitter junction. That's all you really have to do in order to get this device to begin to work. Now, let's go ahead and let's talk about the collector to base junction over here. Now, it looks, and I wholeheartedly agree with this, looks like we got another diode that's been formed, right? We got a PN junction right here. So we have another diode that's been created there. However, this diode is going to be considered different than this diode. And here's the reason. For the collector base junction, this is actually very lightly doped. And remember, when we add impurities to our silicon in order to create this P and N region, we do that by adding impurities called doping when you add those impurities. So this is not the same amount as this PN junction at the bottom. So we can't consider it to be the same as far as the diode is concerned. Okay, so this is very lightly doped. Let's not treat this. Don't treat like a regular diode. Now, what we can say is when the base emitter is forward biased, IB controls the amount of IC. Okay, so this over here is a diode just like we know. However, this over here, I'm just going to go ahead and call it a crappy diode. This is intended to be reverse biased. We actually want it to break down, and that's what allows the current to flow through here. You can kind of think about it a little bit like a current-controlled Zener diode. Okay, for a Zener diode, it's intended to be reverse biased. The same is true for this top diode that's been formed here between this P and N junction. Okay, so you'll see, and I feel like this drawing by itself is quite confusing because you go, hey, there's two diodes here, and this diode would never allow IC to flow through it. Yes, if this was a good diode, but it's not. It was lightly doped. It's a quote unquote poorly constructed diode that's up here, and it's intended to be reverse biased and allow current to flow through it. Now, let's go ahead and let's talk about the emitter collector circuit that we have formed here. Okay, let's talk about this whole circuit. Now, if we look over here, what we have is a collector bias voltage applied to a series collector resistor that's in series with the collector emitter of our transistor over here. So if we talk about this, we have a voltage drop between the collector and the emitter. So we can actually just use Kirchhoff's voltage law over here to talk about this circuit, VCE, the voltage between the collector and emitter, is equal to VCC minus the voltage drop across this resistor. Well, what's the voltage drop across this resistor? It's just going to be IC times RC. So we're going to be using this equation when we go ahead and talk about that collector emitter circuit. I got a question for, can you show base emitter junction definition? Base emitter. Yeah, the base emitter is probably the most straightforward of all of this, because if you look at the base emitter junction, we just have a normal diode that's been created between the base and the emitter. So we have a 0.7 volt forward voltage drop that we need to exceed. So VBB would have to be greater than 0.7 volts. And the amount of current running from B to E is going to be dictated by the value that you select for RB. Now, in reference to this emitter collector circuit, if the base to emitter junction is forward biased, and VCC is sufficiently high enough, then IC will flow. Okay, so all we're saying over there is as long as our base emitter is forward biased and we do have some current flowing into the device, then and VCC is sufficiently high enough, then we will get IC flowing through this transistor. And I think a lot of this will start to make a lot more sense when we talk about the three modes of operation, and we're getting there. Now, there's two other things that we should mention here before getting on to our three modes of operation, which if I have IB that's entering this device and coming out of the emitter, and I also have IC that's entering this device and coming out of the emitter, then the emitter current over here, let me write this in with a different color, IE is equal to IB plus IC. It's just Kirchhoff's current law. So that should make sense, right? These two currents add together inside the diode and come out of the emitter. So the emitter current should always be equal to IB plus IC. And the last thing, and I did mention this last class, which is the relationship between IB and IC. So IC is going to be equal to beta times IB. Okay, this is the natural gain. Oh, this is the natural gain of our transistor, and in this case, we are looking at it from a direct current point of view, a DC situation. So this is the DC gain of the transistor. And normally the DC gain is in the hundreds. I'll just say approximately 100. Okay, so if we have, now this should be in microamps, but if we have 100 microamps flowing through here, we should get 10 milliamps flowing through there. Okay. But of course, that's under the assumption we have forward biased the base to get that IB to be 100 microamps and that VCC is sufficiently high enough so that collector current does flow into the device. So let's go ahead and let's look at the 3 modes of operation that these BJTs can be in. Okay, so this will be the 3 modes of operation. Okay, the 3 modes of operation that this BJT could possibly be in other words, the transistor is only going to be in one of 3 states at any given time. Okay, we call them linear mode, saturation, and cutoff mode. Now, each one of these, the transistor appears to be doing something a little different than the other modes. Cutoff mode could be considered analogous to an open switch. What do I mean by that? I mean there's no base current flowing into it, there's no collector current flowing through it. It's an open switch. Okay, so it could definitely be in this case. In saturation mode, that would be the complete opposite. In other words, we have a ton of base current entering this device, and so this collector to emitter junction is allowing as much current as could possibly go through this device, and so this transistor is behaving from the perspective of the collector emitter as a closed switch, allowing as much current to flow through it as possible. And linear mode is kind of in between a closed switch and an open switch. It's kind of open, it's allowing some current to flow through, but it's not quite closed because it's allowing some current to go through. And yet the relationship is that some fixed number multiplied by whatever's going into the device causes a much larger collector current to flow through the device, hence current amplifier. Now, to make life much, much, much easier with these 3 modes of operation, I'm going to represent each mode with a model. And we're going to use these models in order to analyze any transistor circuit, and we're going to follow a procedural list of steps, and we're going to arrive at the correct answer. Okay, so I find this is the easiest way to actually amplify sorry, not amplify, the easiest way to analyze any transistor circuit is by using these models. At least it's a good way to start off. Now, I think when I learned it, I was not shown these models, and it was just kind of like, yeah, learn how to do it intuitively. I think having a procedural list of steps that we go through and always arrive at the correct answer, you do that a few times, and all of a sudden the whole thing starts to make sense. It does probably appear currently like a transistor is quite a daunting and difficult component to work with. It's really not if we go ahead and just learn these three models. So let's go ahead and let's define our first model. And I'm going to start with cutoff mode. Okay, so we have our transistor, and I'll draw it with a schematic. We have IB, and we have IC. Okay, if our transistor is behaving in cutoff mode, then that means we have zero current flowing from the base to emitter. We will consider it to be open. So IB is going to be equal to 0 amps, and IC is equal to 0 amps. So that's our model that we'll use to represent this transistor when it's operating as inside of its cutoff mode. Okay, now, I mean, that's all there is to say about this, right? Zero current going in, I have zero current going through it. If it's operating within its cutoff mode, then it behaves like this. Done. Okay, let's go ahead and now let's look at the saturation mode. Okay, same thing again. We have a transistor, some IB that's entering, and some IC that's going through it. Okay, if we are operating within the saturation mode of this transistor, then we're going to have two voltage drops involved. Okay, the first one should be no surprise. We have a 0.7 volt drop between the base and the emitter, right? Because internal to this transistor, we have that PN junction that was formed. So we're going to get a 0.7 volt drop from the base to emitter. So as far as a model representing the behavior of this transistor, if we're in the saturation mode, it's going to behave like this. We have a 0.7 volt drop between the base and the emitter. Now we're also going to have a voltage drop between the collector and the emitter due to this poorly constructed diode, this PN junction at the top. And if we're in the saturation mode, we're going to take that to be a fixed voltage drop. It's going to be 0.2 volts. So it doesn't, nothing else in the circuit matters. As far as the collector emitter circuit is concerned, the voltage drop across the collector and emitter, VCE, is going to be equal to 0.2 volts. Hence, the collector current would be purely a function of the value that you have for this resistor up here. And we'll see that later. So this defines our saturation. Okay, so we have two of our three models. The last model we want is something to describe the behavior while this transistor is operating within its linear mode. So same thing again. I'll draw the schematic symbol for our transistor. B, C, and E. We have some base current and some collector current. And now, if we're within the linear mode of operation for this transistor, we are going to get a 0.7 volt drop between the base and the emitter. Let me go ahead and draw this in. However, unlike our saturation mode, we will not get a 0.2 volt fixed drop. We will get a current that is dictated by the amount of base current that's going in here. So in other words, IC is going to be equal to beta times IB. Okay, so these are the only three places that our transistor can be in at any given time. We're either in cutoff, at which point we're behaving like this, or we're in saturation, we're behaving like this, or we are in the linear mode and we're behaving like this. Okay, so once we go ahead and kind of reduce this whole mess into only these three modes of operation, Now we can go ahead and come up with a list, a procedure that we can follow, that we can apply to any circuit that has a transistor in it in order to understand what that transistor is doing. Okay, so let's go ahead and let's call this how to determine mode. I'm going to use a different sheet of paper. Okay, so as I said, a nice list of steps that you follow and you will get the right answer every time. Okay, first off, in a circuit where you have a bipolar junction transistor in that circuit, what we're going to do is we're going to replace that transistor with the linear model. Once you have the linear model in place, solve the circuit, assuming that the linear model is correct. Now, this may require maybe your basic rules, KVL, KCL, Ohm's law, parallel circuits, series circuits, loop, like mesh analysis, Thevenin, whatever it is, it's going to require some application of our fundamental 211 rules, but you're going to replace the BJT with the linear model, and you're going to solve the circuit under the assumption that this linear model is correct. And you're going to check what the base current is. The base current is going to tell you whether this assumption that it was the linear model is correct or incorrect. At which point we'll then decide, do we change that, or is this original assumption correct? Okay, so we're going to check IB. If IB is less than or equal to 0 amps, then the transistor is actually in cutoff. Okay, so let's run down what that means. We start off by taking the BJT out of the circuit and we replace it with the linear model. We're going to make the assumption, it might not be correct, but we're going to make the assumption that the transistor is behaving like this. And then we solve for the base current. If we find that the base current is less than or equal to 0, turns out this assumption was incorrect. Our transistor is actually behaving like this. Hence, IB is equal to 0. IC is equal to 0. And you have to replace the transistor in the circuit with the cutoff model and recompute. Okay? So that's the first thing that could happen. However, it could also be the case that no, IB is not less than or equal to 0. It's greater than 0. In that case, we do have current flowing through. Now, if current is flowing through it, then we may be in linear mode or we may be in saturation mode. We're going to have to do another step to find out which mode we're in. We're definitely not in cutoff mode. If we were in cutoff mode, the IB would have to be less than or equal to 0. So if IB is greater than 0, compute VCE. We're going to need the voltage between the collector and the emitter in order to tell us anything further about this circuit. Now, if you do have current flowing through the base into the transistor and you compute the voltage between the collector and emitter, if VCE is greater than 0.2 volts, you're actually in the linear mode. And since we already started solving this whole thing from the perspective that it was the linear mode, then we already have the solution, nothing further to solve for. However, when you compute VCE, if you find that it is not greater than 0.2 volts, if VCE is less than or equal to 0.2 volts, turns out the assumption of the linear model was incorrect. We were not in cutoff. We have a VCE that's less than or equal to 0.2. Turns out we were in saturation mode. However, our solution that we already have was under the assumption of the linear mode. So we're going to have to take out the linear model and replace it with the saturation model and recompute. Now, it sounds like it's got a lot of steps. They go by pretty quickly. And once you've done this a few dozen times, you can do this in your head. But it's nice to have a procedural list of steps to go through and be guaranteed that your work is going to be rewarded with the correct solution, right? So, okay, I'll run through that over really quickly. Take the transistor out, replace with the linear model, solve the circuit, find IB. look at what IB's doing. If it's less than 0, turns out we're in cutoff. Replace with cutoff and recompute. If, on the other hand, you do have current entering the device, then we need to take one further step, find VCE, the voltage drop between the collector and the emitter. If it's greater than 0.2 volts, we already have the correct solution. We're in linear mode. If, however, you find that VCE was less than 0.2 volts, turns out our assumption of linear mode was incorrect. We arrived at a contradiction. And at this point, we know we must be in the saturation mode. Therefore, replace with the saturation model and recompute. Okay? So it's actually not that bad. Let's do some of these. All right, let us do an example. I shall call this example 1. We're going to have a 12-volt source. With a 2K resistor for that collector resistor and 400K for our base resistor. Emitter is directly connected to ground. Now, let's go ahead and look at this transistor. We have a base, we have a collector, and we have an emitter. And now you look at this circuit and you go, are we in linear? Are we in saturation? Are we in cutoff mode? How much current do I have flowing into the base? Do I have any base current at all? Do I have collector current flowing through this? What's the voltage drop between the collector and emitter? Whole bunch of stuff we don't know about this circuit, but if we apply our list of steps, we'll get the right answer. So let's go ahead, run through our procedure, and see what we get. Okay, what's the first step? Replace with linear model and solve the circuit. All right, let's do it. $12 volts. Going through a 400K. Our linear model says we have a 0.7 volt drop here. And the current is given by the relationship beta times IB. And we have a 2K resistor, and the emitter's tied to ground. Okay, now we're going to need to know beta of this transistor. So actually, in the problem, it is given that beta is equal to 50. All right, so we're going to go ahead and solve this, assuming the linear model, or assuming that the transistor is operating within its linear mode or linear region. Okay, so what's the first thing we want to find? We need to check IB. IB is going to tell us if we're either in cutoff or if we're in these two other modes. So solve for IB. Well, how do we solve for IB? Well, look what we have here. 12 volts, 400K, 0.7 volt drop, and 0 volts, right? Can we go ahead and just do the same thing that we've been doing with our diodes? Absolutely. We have a 0.7 volt drop. We take 12 volts, subtract from that 0.7 volts, apply Ohm's law, divide by 400K, gives us the current flowing through this. So we already know how to do this. Just go back to your LED calculation current through it lecture. IB equals 12 volts minus 0.7 volts divided by 400K. This 400K is the only thing limiting the current going through the base to emitter junction over here. So what do we get? If you solve that out, you will get 28.25 microamps. All right, now we go ahead and ask the question. Is IB greater than 0? Or I should say, is IB less than or equal to 0? No. IB is greater than 0. We're not in cutoff. Cutoff is not what this transistor is currently doing. In other words, it must either be in saturation or linear. I don't know what it is yet. I need to check the voltage between the collector and the emitter. But we're definitely not in cutoff. So we just ruled out one of the three modes that this transistor could possibly be in. All right, we're gonna have to solve for VCE. Okay. How do we find the voltage between the collector and the emitter? Well, look, can we solve for the current? Well, let's put it this way. Can we solve for the voltage drop across the 2K resistor right now? Not directly. So if we want to find the voltage drop between the collector and the emitter, and let me go ahead and write this just to be a little more clear. If I want to find the voltage drop between this point and this point, I would need to take 12 volts and subtract from that the voltage drop across the 2K, right? I would be wanting to use KVL, but I don't know what the voltage drop is across the 2K. But what I do know is that the current flowing through the collector emitter is dictated by this value beta times the base current. And I do have the base current. I already solved for that. And I know what beta is. Beta is 50 because that was given in the problem. So if I do 50 times this, I can find out the collector current. If I know what the collector current is, then I can tell you what the voltage drop across this 2K is because current's the same at every point in a series circuit. So I can then do 12 volts and subtract from that the voltage drop across the 2K once I've found IC. So let's go ahead and let's solve for IC first, and you'll see how that fits in. Now, IC is going to be 50 times IB, given. Okay. Well, what does that equal? Well, 50 times 28.25 microamps is going to be equal to 1.413 milliamps. Once you know the collector current that's flowing through here, well, that collector current is not just flowing through the collector emitter circuit of our transistor, it's also flowing through this 2K. It's going from 12 volts through the 2K down to ground. So now we can go ahead and just apply Kirchhoff's voltage law using the collector current to figure out the voltage drop between C and E. VCE is going to be equal to 12 volts minus 2K times IC. We already solved for IC, So it's equal to 9.175 volts. Okay, so we have a voltage drop that's 9.175 volts between the collector and the emitter. If VCE is greater than 0.2 volts, we're in linear mode. If we're less than or equal to 0.2 volts, we're in saturation mode. Turns out we're in linear mode. And since we already solved it from the perspective of being in linear mode, we already have the solution. Nothing more to do. Everyone good with that? So let me pause here and answer some questions. And we don't have a lab today, so if you can just give me some extra time for lecturing so we can go through 2 more examples, then we won't have to do anything during lab and you guys can leave a little early. But just please give me that time to go over 2 more case examples of solving these circuits. But I want to pause here for a second and address any concerns or questions that you have about how we solved for any of these values and ultimately what's the whole process. Not a big deal, but I got 9.176, not 1.75. Yeah, I'm not going to cry about it. My multimeter doesn't even measure that accurately. And that might be because, I don't know, maybe I used a little more precision for the base current. Got no idea. Does this make sense with everyone, how we calculated the voltage between the collector and emitter? I want to make sure no one is stuck on this basic application of Kirchhoff's voltage law. I'm happy to elaborate on this if anyone has questions about it. Everyone good? I can continue on with the next example?
Yeah.
Yeah, are we doing one of each? Yeah, we totally are. Why would I start any other way than to show one of each, one solution that results with each one of our modes? Okay, let's go ahead and let's do example 2. Beta again is going to be equal to 50. 12 volts. $8.5K, 400K. Notice I haven't changed that resistor that was attached to our base. All I did was change the collector resistor. Okay, let's run through this. Step 1, replace with the linear model. 12 volts. .7 volts between the base and emitter junction. And the collector current is dictated by 50 times IB. And we have an 8.5K resistor. Okay, easy. We already know how to calculate the base current. First thing, we want to figure out the base current. Find out, is it greater than 0 or is it less than or equal to 0? Okay, well, we already solved for the base current, and it's going to be the same as the previous problem. We did 12 volts minus the 0.7 volt drop created by the PN junction between the base and the emitter, and divided that by 400K using Ohm's law to get the base current. So we know that IB is going to be greater, let me do this. IB is going to be equal to 28.25 microamps. Go to the previous problem if you want to see how that's calculated. And IB is definitely greater than 0. Not cut off. Cool. So now we need to figure out VCE in order to find out if we are in saturation or linear. Okay, we ruled out cutoff mode. However, to find VCE, we're going to have to find IC first. IC just equals 50 times what we already solved for IB. Okay, so we find out that IC is equal to 1.4125 milliamps. So now we can use Kirchhoff's voltage law, do 12 volts minus the current times the resistance here. It's just applying Ohm's law to get the voltage drop across the collector resistor. 12 volts minus the voltage drop of the collector resistor gives us the remaining voltage, which is the voltage drop between the collector and emitter. So VCE, therefore, is going to be equal to 12 volts minus 8.5K times IC, which equals minus 6.25 millivolts. All right, that's a problem. Last I checked, we have a higher voltage on this side than on this side. Why are we getting a negative value? We arrived at a contradiction. We worked off of the assumption that this transistor was operating within its linear mode. Turns out it's not true. When you go ahead and solve it as though assuming it is within its linear mode, turns out you get nonsensical answers. Well, we know it's not in cutoff. We know it's not in linear. It must be in saturation. It's not in cutoff, not in linear. Therefore, must be in saturation. Take the linear model out, put in the saturation model, recompute for the real answers. So we have 12 volts, 400K, For the saturation mode, we still get a 0.7 volt drop between the base and emitter. However, in saturation mode, instead of the collector current being controlled by the transistor, this transistor is behaving as closed of a switch as it possibly could be and allowing as much current as is possible by the circuit to flow from the collector and the emitter. So the current is no longer controlled or dictated by the transistor. So remember when I first started off talking about a transistor, it controls the amount of current between the collector and emitter. But when you allow too much current to flow, all of a sudden the transistor is not in control of limiting that current anymore. Instead, it's now this resistor that takes precedence. So we get a fixed 0.2 volt drop. And now, what is our collector current equal to? Well, let's go ahead and what's different from our original solution? Has the base current changed? No way. The base current is still 12 volts minus 0.7 volts divided by 400K, which gave us 28.25 microamps. So IB hasn't changed. Okay, what was the other thing we solved for? IC and VCE. Those two definitely changed. Let's start with VCE. What's VCE equal to? .2 volts by definition. That's a given from the model. The model, when this transistor is behaving in saturation mode, is that the voltage drop between the collector and the emitter is 0.2 volts. So VCE is equal to 0.2 volts. Okay. What about IC? Well, IC is not governed by the transistor anymore. So IC, we're going to have to compute. Well, that's actually pretty easy to calculate because I have 12 volts minus 0.2 volts gives me the voltage drop across this resistor. Take the voltage drop across the resistor, divide by 8.5K, and what do you get? The collector current. That makes a whole lot more sense. This made no sense because our assumption of linear mode was wrong. However, once we rule out cutoff mode and linear mode, what's left is saturation mode, and we get what makes perfect sense. 1.388 milliamps of current flowing from the collector to the emitter. Everyone good with that? So now let me go ahead and point out something. Once we've done 2 of these thus far, now we're starting to gain an idea of what it is we're trying to find. We're interested in the base current, we're interested in the voltage between the collector and the emitter, and we're interested in the collector current. These are kind of our big 3 values that we're interested in solving for. Let's assign a name. We're going to call these 3 values put together the operating point. What I mean by operating point is this transistor has the ability of being all over the place. It can be in linear, it can be in saturation, it can be in cutoff, it can be in saturation, and it can be in various degrees of linear mode. So we have a point along some future graph that we're going to look at that defines all possible operating conditions of this transistor. It's given by these three values. So let's go ahead and get in the habit now of referring to these three as our operating point. Okay, any questions with this one before we move on to our last one? Let's see, we've done linear, we've done saturation. Good bet this last one's going to be cutoff mode. No questions? Huh. I actually lied. I don't have an example with cutoff mode. I'll have to make one. Let's see. You know what? Let's just take this same circuit. And I only have to change one thing about it. Okay, give me a voltage up here that makes this transistor behave as though it's in cutoff. Greater than 0.7? Less than 0.7, right? All right, what happens if we have 0.5 volts up here? Okay, let's run through the procedure. Replace this with the linear model. Okay, I have 0.5 volts applied to this 400K and a 0.7 volt drop between the base to emitter. What does IB equal to? Yeah, the base emitter junction here isn't, it's, I guess it's forward biased, but it hasn't exceeded that forward voltage drop, so IB must be equal to 0. Right? If we don't have a voltage higher than 0.7, we're not going to get any current flowing into that base emitter, right? Okay, so we're in cutoff. Replace with the cutoff model and recompute. Okay, let's solve for our operating point. These are the three things we're interested in. Let's start with IB. What does IB equal to? Well, it's 0. It's open, right? Our voltage applied never exceeded the 0.7 volts required to get a non-zero IB flowing into our device. So IB is equal to 0. Okay, what's IC? Well, with an open circuit between the collector and the emitter junction, I'm not going to get any IC. IC is also equal to 0. Now, what's my VCE? I will caution you. It's not just 0 because everything else is 0. We have a potential. We have a voltage coming over here. What is it? 0.5 volts. Remember, we have 0 current flowing through this. We get 0 voltage drop across the resistor. But we have 0 volts on this side. We have 0.5 volts with a 0 volt drop. So I have 0.5 volts here. I have 0 volts across the collector emitter. 0.5 volts across the collector and emitter. So VCE is equal to 0.5 volts. That's what I end up getting. Okay? And I guess if you want, you can call this example 3. Okay, everyone good with that? Okay, so if you noticed, applying that procedure is not difficult. You just kind of have to remember what it is you're trying to do. Substitute for the linear model, or I should say assume that the linear model is correct until you arrive at a contradiction. If IB ends up being less than or equal to 0, then we know we're in cutoff. We're replaced with the cutoff model, recompute. If, on the other hand, we do have base current flowing, then we must be in linear saturation. Compute for VCE to determine the difference. And then if we're already in linear mode, we have the correct solution. Otherwise, if VCE ended up being less than or equal to 0.2 volts, then we were actually in saturation, replaced with saturation model, recompute. When you get more comfortable with this, you can kind of do a little bit of this in your head. Look over here. 0.5 volts. Subtract them from that 0.7 volts. Divide by 400K. Well, I haven't exceeded 0.7. So I know we're in cutoff. I didn't really need to draw all this. I just had to look at this and go 0.5. Oh, 0.5 is not greater than my 0.7 volt drop between the base and the emitter. Therefore, I have 0 IB. Therefore, this must be in cutoff. Okay, now let me go ahead and either draw this or think about it in terms of this, and you'll arrive at the correct answer. Same thing over here. Okay, 12 volts minus 0.7 volts, divide that by 400K gives me IB. IB is greater than 0, okay. So we're definitely not in cutoff. Now let's go ahead and solve for VCE. To find VCE, I'm going to need IC. So I use these models to very formally and explicitly help people out. But once you get comfortable enough, you can see that they're a little redundant here and there. Okay, so this is just a tool to get at the right answer no matter what. Okay, and then once it starts to click, once it starts to make sense, you can back off from overusing the models. Does that help? So if anyone is wondering, like on an exam or quiz or anything like that, and they go, well, do I have to draw every single model? No. You just have to give the right answer, which is what mode we're in, what's our collector current, what's our IB, what's our IC, and we'll next time learn a couple more things that we can solve for. Okay? So I'll hang around for a little bit, but aside from that, you guys are free to go.